So let's continue now with our first order nonlinear PDE. So just to recapitulate, we have this. The PDE written in implicit form. This chalk is right. So can you read it from the back? Is it readable? Yeah. Okay. Good. It looks not too white. Good. So and then we say, hey, how to get a quick review? This one looks better. This chalk. This is what I want. Geometrical info, right? Information as before. How do I get it? Well, then we said, okay, we just changed the notation a little bit. But let me already, no, let me do it like this. And we're going to parameterize like this. Then we say, okay, let's look in the neighborhood. So this is a little bit, okay, let's put it like this, like quick review of the story. So this is near P0. Right? And we have here a normal, excuse me, where the normal to the surface, the integral surface is this. So very quick, right, review what we saw last time, and which I said, right, many times, I think it's fun. You look at this and say, wow, how do I take geometrical information out of it? But then that's why we also learned the quasi-linear case, because it helps us. There's no inner product here, but the normal is still there, right? As soon as you change this notation, as I mentioned, the -1 we don't have to keep. And this is just a relation, right? This is a relation between, for a fixed point P0, at a given point P0, and we're going to look in the neighborhood, at the neighborhood of this, in the neighborhood of this point, or first at this point, this question becomes, how can I get, if I choose P to be my parameter, I say I'm going to try, right? It's all, as you will see, it's all like attempts to put things together and see if it works. It works, which is now, let me get P, Q in terms of P, which, because these two guys are tied together because of F. Right? So I have a relation, an implicit relation between the two of them. I choose P as the parameter. I get Q. If I can solve this, I get Q in terms of P at the point P0, which basically means I'm getting the candidates, the possible normals at that point. And I said, we're going to, for a while, live with this ambiguity of normals. Well, if we have this ambiguity of normals, then, oh yeah, then first, before we do that, then, well, if instead of thinking of normals, it's the same thing, I'm going to think about tangent planes. Because a tangent plane, a plane we define its equation as a normal, or a normal has, who cares, right? So it's better to think about tangent planes. And therefore, let's see what I wrote last time. Oh yeah, so then with tangent planes, with all these candidates, tangent planes at this point, and remember I put my sheet of paper on the bottle top because somebody asked me, oh, why do I have to look at half the plane? Well, half the plane if it's, I'm rotating this, but if it's like that, this is the point P0, right? And if I do this and I look at half here, I get a cone, right? A cone with a vertex here and another image over there. We don't care, right? So at the point P0, we get the Monge cones. Do not have to be circular cones. I just, for simplicity, I draw it like this. Where here is a tangent plane, right? A little, just miniature plane. It comes all the way up to here, right? But with the, right, oops, so that we can see it better with the norm over there. Okay, we did one example. I'm going to skip that. I mentioned about having a field of cones. Okay. I just want to write something. Here it is. And then finally, I have this. Where H is right, my family of planes, and from here we have two equations, which basically I call this the initial PDE. This is my family of planes, and if we look for the cone, comes out of the envelope of this, right? And there's the envelope condition, right? Gives us the cones, right? I'm going fast, but you have last class to review, and it's recorded. There's the notes and everything. Okay, then we made an example of a cone at the origin, and now, okay, good. And now starts today's class, right? The lecture, which is still, I think it's very much fun. Seriously, the first time I studied this, as I mentioned to you, I spent a lot of time reading, not all the details in the books and so on, and fascinated how to get the characteristics out of our geometrical interpretation out of this guy. And we're going to see it now that we're going to get actually 5 characteristic equations instead of 3. That's the difference between quasi-linear. And at this point, you can start believing why it's going to be 5, right? I mean, you should once in a while believe what I say, right? But not fully trust it, because you got to confirm and read. But why is it going to be 5 characteristics? Well, we have one for this. Let's put it here, because we write in terms of z, right? We're going to have dx dt, whatever the parametrization is, dx d tau, dx ds, but S is for the gamma. Doesn't matter, right? I hope I don't mess up with the parametrization, but it's easy to figure out. So we're going to get, let's call it t, dx dt, dy dt, dz dt, and you're going to see I have to evolve these guys too, right? And I'll draw a very cool picture. At one point, it's in the notes best done, which is it means like evolving the plane. So you have this curve x, y, z in 3D, and you have to evolve these planes. Say if the characteristic go in this direction, you're going to have an evolution of planes along this line. What is the evolution of planes? It's the evolution of its normal, right? And to evolve the normal, I have to evolve only P and Q, because the -1 is always -1, right? So we'll see this. So let's prepare ourselves then to formulate the characteristic system of ODs, okay? Okay, so let's see what we're going to do. First, let's look at this. We have the planes. The equation for the planes. And from this equation here, we get So this equation here, let me get it right. We're going to use it at a certain point. So this we're just using the planes. Now, to obtain this guy, and soon we're going to cook up the characteristics, okay? To obtain dq dp, let's use the PD. So let's take, if we're thinking that P is our parameter, let's take, the total derivative, right, of PF with respect to P. So this is df dP plus df dq dq dP, which should be equal to 0. Right? Because not of this one, but the equation, this is H, sorry. I pointed it wrong because of, right? F is identically 0. And this is just to remind us that we're doing things locally. Okay? No big deal. All very simple. And also to set notation. So if we substitute, if in the envelope condition, right, that's the condition for the envelope, we get, let me skip one step because it's simple. We get that and let me highlight this because this is important, right? Or, doesn't matter, FP over FQ okay, so this just came from substituting, differentiating the PDE, right? Remember that I can write the PDE like in a super condensed form like this, right? It's identically 0, so it's like a level curve of this implicit formulation. So if I substitute what I got from the PDE, this guy here, into the tangent planes, I get this. So can you see a characteristic equation arising? I'm forcing it, of course, but this, like, to get us a little bit ahead, right? You see, in the neighborhood of this, if this becomes like a, just think of this, this becomes a little bit like a dx. This becomes a dy, right? We're already going to see that somehow the dx dt is going to be fp, the dx dy is going to be fq, and with which for the quasi-linear equation, it's going to be a and b. So, of course, we can do the consistency check afterwards, okay? But no big deal, right? So this is the first one, arising. Then, using, let me see if I can use it. Let me try to use this blackboard here. Substituting above, which is in the tangent plane equations, blah, blah, so I don't have to write too much, so we keep space. We have this. Let me copy so I don't make mistakes. Okay, so can you see? This is just substituting above. Where? In the equation for the planes, right? Substituting the things we've got, boom, 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 and just pile it up, organize it in a way that's interesting. Interesting, why? So you see sort of ratios of these guys, which we just saw above and below. So when this becomes, this will eventually become like a dz, this will become like a dy. And we can see here, look, from here, I already sort of inferred to you that the dy, blah, 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 whatever parameterization I choose, the vector field for the characteristic is going to be fq, so it is here. And therefore, the dz, the vector field for the dz, is going to be this guy up here. Okay? So like this, we start cooking up things that look like the characteristics. So adding all these together, putting all this information together, right? I can see from your expressions that what I'm going to write now, you already saw it, but just for completeness, right? So putting all this information together, we have that. So I can write this. Right? If you take the limits, the point approaching, just putting these ratios, right? And I skipped, I think, maybe one line from the notes. Okay. No big. So therefore, let me put here, we have like an incomplete system of characteristic ODEs. I'm using d tau just to be okay, so and I put in the notes here a little message to you, like double check this for the quasi-linear equation, right? The quasi-linear is going to be a du dx plus b du dy minus c equal to 0, right? Because I put the c over here, and that's the f, right? And then do df dp, look, aux, so it's ap, let me do it by, so it's going to be ap plus bq minus c equal to 0, right? So df dp is a, df dq is b, right? So very simple to check. It's got to be consistent, of course. And now we have to, let's complete our system, since we need ODEs for P and Q, right? That's the stage where we are right now. We need an ODE. We need to complete this system with an ODE for P and Q. And then we're also going to, for the Cauchy problem, we're also going to have to do a little work, a little, monkeying around with things. It's just like playing with things so that we can get the quote-unquote initial condition for the ODEs, because we have f of s, Cauchy problem gives us f of s, g of s, h of s, which basically gives us initial condition here. I mean, conditions here, right? If we think of initial conditions here, or at least initial condition in the sense of propagating out of the Cauchy curve gamma, right? So we need initial condition here, initial condition here, initial condition here, but then we're going to need equations for P and Q and conditions for P and Q, because the problem does not give us conditions for P and Q. But we're going to be able to compute them as long as gamma is not characteristic, right? But now that's kind of getting intuitive for us, right? So that we can get out of a curve gamma, gamma cannot be characteristic. So, okay. So let's go. On a characteristic curve, gamma, we have this. Right? All I'm doing here is notation. I'm saying on a characteristic curve gamma, suppose I solve this, I have x of tau, y of tau, and this will tell me how P and Q are evaluating along that orbit. Now, you might say, where is Z? No, Z is somehow here, because remember that this is U of X, which would be like Z of X, right? And this is U of Y, right? And our solution is U of X, Y. Right? No problem. Okay. So therefore, dP d tau, which is what we want, but we don't know what now we have to find out what is the proper vector field for this guy of the ODE system, which will depend on the vector field of these guys once I do chain rule, right? So it just gets messy, but it's putting information together. Okay, so this is P of X, dx d tau, P of Y, dy d tau, it's this, which here, let me use a space, this is just going to be P of X, f of P, P of Y, f of Q, Q of X, f of P, plus Q of Y, f of Q, using already the information from the characteristics. Okay. So then, it looks like we're getting stuck. Not really, right? We need to know these guys. Right? But this is ultimately what we need is this guy, because this is how we sort of flow, right? Which sometimes they say evolve, but flow, right, along a characteristic. These will depend on these guys, but these guys here, basically we can sort of maybe cook up, right? Extract this information from the PDE, right? Maybe differentiating things, differentiating the PDE. Mainly, well, it's right over there, so we'll do it. So let me use this space here again, because it's good for the video, so we don't keep on going back and forth. Okay, so where am I? Okay, so let's use here. df dx is f of x plus p f of u plus f dp plus q of x, x cubed, df dy will be similar, f of y plus q f of u plus q of x. Oh, got it wrong. Y, p of y, f of p plus q of y, f of q. Yeah, dq dy. Okay? But some of these fellows we already have. Now maybe I should go to the other board. Now I need to do just some, it looks like it's getting, not really complicated, it's just getting messy, right? We have to organize things. And we can see, for example, things like we're getting here and there the derivatives of second order. So we're going to admit C2, right, for f. Let me write it over here. Not for f, for the function. So let's admit that we have, and let me write like this, right, which is equal, right? So we need C2 so that u of xy is the same as u of yx and da-da-da, so we can play with these guys, right? So assuming regularity of our solution, then let me see. Oh, I see what I'm doing here. Yeah, I forgot something here that's important, right? So I hope the video can follow me. This is equal to 0 and 0, right? If I hadn't written that, no problem. So since this is equal to 0, I can put something on the right-hand side, the left-hand side, right? So this is here, 0. This is what I'm going to write here. And since I didn't do that, I wasn't understanding my notes. So I can write this. Let me write and then double check with the board, see if there's no mistake. So this is just like tedious calculation. Okay, let me double check if I wrote this right. F of x, P of u. Yeah, so basically here, right? This guy here, we put the other side, right? The same thing, this guy here. We'll put on the other side. Okay, this is equal to py, right? One's equal to qx. And therefore, what do we do here? Let me ask you for your help. Because it's like, now it became a little bit of, just as we say sometimes in Portuguese, trabalho de braço, arm work, right? Just gets messy, but if we do the housekeeping, organizing things, then things collapse and become not so messy, right? So chain rule, chain rule, chain rule, looking for what I want, blah, blah, blah. So right here, look, we just got to remember what we were looking for, right? We were looking for, say, these guys. And this guy is the same as this guy, and that. So basically, it's almost like we have a linear system to solve, right? This guy is okay, right? We have it. And therefore, so, let me put this way. We have now our characteristic system of ODEs. And let me write everything again because it looks nice. So we can see everything together. FP, FQ, PFP plus QFQ, okay? And these guys come from the calculations we're doing upstairs, okay? You might be skipping one thing or the other, it doesn't matter. Basically, the road has been paved, right? It's just a few details. So now we have ODEs, a system of ODEs. Now, 5 by 5. We got how P and Q will evolve along a. So let me, good. I was almost going to make a mistake, which is not a mistake. Let's make an agreement. It's a little bit like simplifying a little bit the terminologies, right? Which is, this is the characteristic equation, right? But since this expresses, it's good I caught myself almost making something that is imprecise, but it's okay. It's okay if you do it too, right? When you write down exercise. This is the characteristic equation, but what I will call the characteristic is usually the orbit, right? So it's going to be what comes out of this, which is x, y, z exactly, just like you did with your hand. Some curve here in space, in 3D space, right? So again, these are the characteristic equations. When I talk about the characteristic, it's this orbit. The characteristic projection is on the horizontal plane, because this could mean space, time, and wave elevation, right? You're with me, right? And this is still part of the characteristic equations, but it has to do with the normal of the plane that's sort of surfing, that's sort of going along this orbit in 3D, okay? I'm going to draw a picture about this, which we have. So characteristic system of equations, and the characteristics are here. We have initial conditions for the characteristics, for the orbit, but not for this. So we have to do this. So this is called Sharp-Pitts equation. In some place I also saw it called Lagrange Sharp-Pitts equation, right? When I learned this, it was not attached to the name Sharp-Pitts equation, so I don't know which is the most common way of calling it. And we might call it, I wrote here in the notes, I think this is a law. This is a good way of saying it. That's why I write in the notes for me not to forget to mention it. Is a law of propagation of characteristic elements. You see, and so this is a little more general than just the characteristic. And characteristic elements, because we're going to call these little planes that I drew over there, plane elements, right? Like a little tile, right? That will sort of approximate our surface. And these tiles, right? Like in Portuguese, ladrilho, right? These little tiles will propagate along this orbit, right? And then as a first approximation, the integral first surface looks almost like the skin of a fish, right? Sort of smooth, but one little piece on top of the other, but that's an approximation, right? Because it's tangent to the plane. But that's a good way of having an image in our minds. Okay, so let's see how, right, let me make so I don't have to move too much, go to the other board. So we have here the Cauchy data, as I already mentioned. Okay, the Cauchy data. And we need to find I just found a small typo in my notes, which I wrote. We have to find P of S and G of S. It's not G of S, it's Q of S. Right? It looks so fast that the G looks like a Q, but you know. And if you find typos in the notes, let me know, okay? Because I've been trying to type these notes up. So, okay. So this is the data I need to find. Okay, so I think it's not going to be good. Let me go to the other board. Unfortunately, we'll move, but if I have, I'll rewrite some things for the video to keep track of things. It's very good to lecture on a big board, but sometimes we get far apart. So let's see how we can get P of S and Q of S. Okay, so let me write this. So let's consider, that's the best way of saying it, let's consider the following system. Let's see if I can motivate it to you, okay? Let me write it in silence, and then I'll explain in words. Because at first it might look a little artificial, but it's not. And it has, we can give names to it. This is one piece of our system. Okay, here's another piece of the system. And let me put a little note for us, maybe here, observation. I think it helps. At least it helps me. Okay, so if I leave this here, let me take a little drink of water. If I put that over there, what am I saying? I mean, these are what are these conditions saying? And they're going to have names, and actually, this whole thing together is going to be called. Let me put it here. I didn't even have space, but it's okay. I mentioned this a little bit last class. This is going to be called the strip condition. So again, right, as everything in which I like a lot, this is very geometrical view. So it's a strip in the sense of a strip, like right. So why this condition? What this condition does? Well, I have two guys that I need to find, P and Q. So usually maybe I might need write two conditions to see if I can nail this. The first one is what I nickname, right? It's an informal terminology, that's why I put quote unquote, the initial PD, right? I nickname it like that. I think that you don't even find in the book, because it's initial, because I mean, quote unquote, because not necessarily I have time, right? There's time in the problem. In the Icono equation, there's going to be no time. So this is basically the initial PDE, which is, let me put it here so sort of it helps. Evaluated along the Cauchy curve gamma. That's why I call it initial, where I'm starting to solve my problem, right? So pick an S, you're basically evaluating on a P0 or whatever other one. So boom, 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 boom. So if I can, so if I have some sort of initial curve, right, I'm going to evaluate the initial curve, but right now I don't know who these guys are, right? That's what I'm trying to find. So don't be fooled by the notation, right? In the sense that I don't know it yet. The system is to find these guys. This other condition here, which has a geometrical information, is basically doing the total derivative of u with respect to s along that curve. This is chain rule, okay? But it's an interesting thing, because look at this. it means exactly this. Do you agree? An inner product. So the chain rule of u along the Cauchy curve has a geometrical interpretation because it's basically this by definition. If you think even, right, whatever you choose your permutation, but if it's arc length, it's even better. This is a tangent vector along the curve, right? Parameter. And this, by definition, is the gradient. It's the normal one. So it's just, right, the -1 is here, if you put that over there, right? And this is dz/ds, right? So this is basically this information about tangents and normals. This is the PDE. And from here, right, solving, this is a nonlinear system. For P and Q, right, along the curve gamma. And let me put it here as a remark. If possible, sometimes it might not be possible, then we have a bad problem, right? Things don't. So if possible, this leads to finding P of S and Q of S. We'll see concrete problems where we have to do that, right? And one is actually when we get to the Iconal equation and so on, which is quite fun and related to waves. So one way, another way I wrote down here, another way of saying the same thing, which is good to write, is this. This gives us this is a good word, right? Sometimes I forget the good words as I'm writing it. Admissible tangent planes along gamma forming a strip. So the two good words here are admissible tangent planes forming a strip. Let me make a picture here. Maybe it's in the next page. No, it's not even yet, but I'll make it here because it's good. So if we have okay, so here's our integral surface. Here's our Cauchy curve, right? Eventually, we're going to have here the characteristic. So this is in the direction tau. This is in the direction s, right? This is my point for a certain s. And if I have, once I have P of S and Q of S, I have a normal here. Right? Is it too small for you to see? Is it too small? No? Okay. Let me make it bigger maybe. Let me make it bigger also for the graph, for the video, right? So I'm put here more in the middle. Cauchy curve, maybe a characteristic in the tau direction. And here at this place here I have a plane right? This plane is tangent to the surface at the point P0, right? So this guy here, like expressed by this guy here. Let me say if it's S0, it's like this. So this sort of vector with 5 pieces of information is telling me a lot in terms of geometry. It's telling me at the point P0, I have this tangent plane. The tangent plane because of the normal PQ minus 1. So the picture is this, right? Now, if I go to another point here, I'll have the same vector, but with S1, 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 S1. And that will give me another tangent plane with, say, another normal. Right? So therefore, this is called the strip condition. I've got to be careful with the Brazilian flag here. So this is the strip condition because this is the strip. Can you see? A bunch of planes, boom, 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 a continuum of planes as this point S is sliding over the Cauchy curve, right? So it's like my notes here, like this, right? Sliding along the Cauchy curve, right? So therefore, that's why it's called the strip condition. This is the strip, right? And this basically gives us, this basically gives us a plane element, right? At the point S0, I have the point P0, the normal, so it's a plane element, a little local tile that's tangent to the surface and sort of locally expresses the smoothness of this surface, which is the plane varies smoothly in terms of its normal, blah, 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 blah. So that's the story. So this is how I get, eventually we'll do a concrete PDE and see how we get these guys, how easy or how difficult it is to get what? To get the initial conditions for P and Q and then to solve the characteristics. And there are problems where we're going to do the whole thing. Okay, is this clear, this picture, why it's called strip condition? Okay, and I think one more information is that, well, admitting, I'm saying here in the notes, admitting that we can solve the 5 ODEs, system of ODEs, and together with the 5 initial conditions, again, we need this to hold. So let me write this here. We have the same condition as for quasi-linear PDEs in the sense that dx ds f of q dy ds f of p be different from 0. What condition is this? Is this indeed the same condition we had before? I mean, it looks new. It's a condition with a new sort of dressing, a new notation, right? What condition is this? In words, what does it mean? What is it important? So let me give a little bit of time of thinking, right? dx ds, f of q, dy ds, f of p, different from 0. I need this. So what is this? Right. So the Cauchy curve gamma is not characteristic, right? It becomes evident, right? If we see, for example, we can see this in two ways. This is dx d tau, dq dy d tau, and this means the Jacobian of the change of variables from xy to s tau, meaning s tau, right here it is, s tau, right? So locally solved. So this has to do with the Jacobian or the curve not being characteristic. And if we think also another way of thinking, which was the way I thought first here, right, is also that, well, f of p is A, f of q is B, right, which is the vector field for the quasi-linear equations. It's the Jacobian, so very good. You identified it, right? Things might change the notation here and there, but who cares? If we don't memorize the formulas, we know what each one means geometrically, right? We then say, oh, okay, this is actually so that we can solve the characteristic equations and come back to our original variables of interest, y and x and y. Okay, so let me basically redo a little bit this picture. There's a picture in the notes. So this is the picture geometrical picture of solving the characteristic system. So we're going to have here so I may call this the initial strip. Right? This is the curve gamma. And here I'm going to have this. This is our characteristic strip. Yeah, and I don't think I have to write much more for not to get this very easy. So this is a little picture that tells exactly what the Cauchy problem is about. Is that okay with you? Let me say it more, just make sure, right, things are complete. I have my initial curve, right, where the initial curve is this, right? I say, okay, Cauchy problem, right? I have my initial curve, which is this. Then from the initial curve, we have to get, so this is like our shopping list, right? I give you the Cauchy problem, or we're given the Cauchy problem. We get the Cauchy curve. But we know from what we did there that our system became bigger because the problem is nonlinear. So I said, okay, I have the Cauchy curve. I need to get the initial or the Cauchy strip, whatever you want. So we use the strip condition to give us P of S, Q of S, strip condition over there, which is initial PDE plus the chain rule of U, blah, 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 which means you get an inner product of the normal with the tangent field, okay? So, okay, once I have this, right, the strip condition, which means I sort of understand what's going on here. That's why it's called strip condition, so very, very intuitive geometrically. Then solve characteristic equations to get the characteristic strip. But this is happening sort of all over, right? I'm solving the characteristic system of equations. It's a one parameter family of ODEs. So I'm solving for this point, for this point, for this point, for this point. So it's like approximating the initial, like a fish, right? Approximating the integral surface locally with these little plane elements, right? And so on. So that's the geometrical picture, right? Eventually, we're going to get analytical formulas, right? And which gives us the integral surface as it is. So, as I mentioned, this quintuple is what we call a plane element, or the tile, as I mentioned to you, right? Okay, let's see my notes here, what else I should say. Okay, an observation. I already sort of mentioned it, but let's be complete. A note or an observation is that sometimes mentioned as an integral of our system in the sense that F is constant, right? Simple. That's how we set the PD implicitly. And actually, if we do the total derivative of F with respect to tau, this is, right? It's just no big deal, easy to believe, but you can check if you like. So the simple check, right, just is that substitute here the characteristic equations to see what this is equal to. It's going to be equal to 0, which means F is an integral and it doesn't vary along, will not vary along the characteristic, right? So very simple, easy to believe. There's another thing. Yeah, maybe I can use this board, trying to be economical with boards so that the video doesn't have to follow me too much. So if I do this picture here, And I have a characteristic here. Yeah, the picture in the notes is not so good, but it's okay. Picture is not so good. In the notes also, it's not as so good, but I think it's a little better. This is what I want to say. But I think you understand. From what we got up to now and seeing the expression in your faces, you're going to understand. So here's a gamma curve, right? Let me put another one maybe here. And this will become more intuitive later on, right? But right now it's a little bit like, okay, André, why should I care about this? You see, with the Eikenhoff equation, we actually have an expression for waves. But I can sort of stimulate it now. So take this element of plane, which is tangent to the integral surface. Okay, it's tangent to the integral surface. So if I think of this locally because the integral surface is smooth, right? Locally, the plane is a good approximation to the integral surface. So if I cut it sort of like this and I project it down onto the horizontal plane, I have this line here, right? So this is called a line element. Okay. So then I have this other, right? I have this sort of, let me do a picture like this. This guy's evolving along the characteristics. So it's changing, right? The normal is changing. It could even be doing like this, whatever normal change. And this, if this is approximation of the integral surface, if I cut it in a vertical plane trying to get a level line, because as I see it projection down there, I see these line elements. You will see, you have no reason to maybe to believe me right now, but you'll see probably maybe soon in the course that when we do the Eikenhoff equation, these are what we call lines of constant phase. And this is like if you see a picture of the ocean, and because of the sun from an airplane, right, you see the crests of the waves as being like almost like locally straight lines, because that's where the sun shines differently, right? And the trough of the wave, which is what we call in Portuguese cavado, sometimes is a different color from the crest. So if you look from an airplane or from a satellite pictures also, you see waves in the coast as these sort of ripples, these lines, right, which we call phases. So I'm already preparing your mind for applications of waves and what we'll see in the near future, which is we're going to look at waves and we call the phase of the wave in something related somehow in a trigonometric sense. Think of a sine. Okay, maybe I'll put a drawing here. Okay, think of a sinusoidal wave, which is a cut sideways of the wave. This are the same, are sort of similar phases, because that's where sine is equal to 1. So say pi over 2, 3, right? And there we go. This is another phase, let me put it like that, which is where I keep on saying pi, where sine is equal to -1. Okay? And it doesn't have to be there. So this is another phase where it's the same height. Okay? And if I have a wave, let me do maybe a better picture here. Right? This is kind of a reasonable 3D drawing of a sinusoidal wave moving, say, in this direction towards the coast. And if I put in red the places where it has maximum height, and I put in white the places where it's -1, you see from the airplane, I'm going to see straight lines, red, white, red, white, red. So these are what we call the phases, okay? So why am I saying this? Because these line elements, which here are abstract geometrical features, which are a little bit, if you cut this plane element like this, they can be interpreted, and the problem we'll see in the future, as exactly this, the phases of a wave seen from an airplane, and which it can change direction. You will see this. It can change direction. You see this in not much detail. We see more of this sometimes in the fluids course. No, but you will see in reasonable details that these lines might change direction depending on the depth of the water. Because depending on the depth of the water, the wave propagates faster or slower. Actually, the wave propagates slower in shallow water and faster in deep water. Okay? And that's actually one of the reasons, let me maybe, since I have some time, mention, that's why tsunamis get very big close to the shore. So since I have time, let me give you a little bit of an application now, right? Why not? So look at this. If I have this, okay, this is getting shallow, and I have this wave here, okay? So a tsunami, I'll come back to this, but since I have a little bit of time, why not? So I can finish at a good point to continue. So a tsunami sometimes is 50 to 100 kilometers long, right? Because there's this underwater earthquake that shakes the water over a large region, right? So it has, and the water here is very deep, right? And usually the amplitude of a tsunami when it's generated, it's not much, like a meter, meter and a half, over 100 kilometers. So from the satellite, you cannot even quite see the slope of it. It's varying very slowly. But then, since it moves slower here, right, this is what happens. It's moving slower. My drawing is not very good. I'm going to make it, because the front starts going slower than what's coming in the back. So it piles up. So due to conservation of water, right, of mass, this has to increase, right? Because this, think of this whole amount of water, right, now is only over a very, let me exaggerate more, is over a very small region. And that's why the wave suddenly becomes 10 meters high or even more, right? So this is one of the effects, because it propagates. And you see that the phase here is varying, right? The phase was equally spaced, like here, and suddenly here, it's not anymore equally spaced. It's like from the airplane, we would be seeing something like this. You agree, right? Because the crests are getting closer. We don't see the wave height here, but we see, and this is what we're going to learn with the Icono equation, which is a nonlinear example that's very useful, to be seen soon, okay? So, so I started this whole illustration because of this, which here was quite abstract. So the projection of a plane element down there, right, is basically a line element, which is just cutting a single level, which has a physical application. It's things like that. Or even more, if it's coming near the coast, sometimes you see it like this. Look. No, let me do a better drawing, since I have a little bit of time. You sometimes see things like this. And I will ask you, where's the beach? We're in Rio. We better know all the time where the beach is, right? So where's the beach? It's basically somehow around here, right? Because the waves tend to come. And here you see that there's some sort of depth variations. And this is one of the last things of the application I want to mention, is that this whole thing here and the way this ray curves, This is the characteristic, and we're going to see that this is called in water waves geometrical optics, because it has an analogy with optics and with index of refraction that we know from optics. Okay? I mean, I see some of you look puzzled, so don't miss the next classes, right? I can't tell you anymore now. Right? It's a good advertisement for it. Don't miss next class. This has to do with optics. Okay. So I more or less went through things I wanted to say. Let's see if there's any more. Oh, no, this I already done. Wait a minute. Oh no, this is an example. Okay, so let's just do this example, okay. And then, I mean, or at least indicate the example started and we'll continue. Okay, back to this example I did last class, nonlinear equation, but now I'm giving you Cauchy data, or initial condition in this case. This is the F we have. Okay. What did we do last time? We saw what the Monge cone looked like for this guy. Now, we didn't have the characteristic equations. Now we have the characteristic equations. Okay, and for this equation, right, just use this, P, not P, Q and P, of course. Q, P, this one's minus 2PQ, this is 0, this is 0. Okay. So y is actually t, no big deal. So we have to work on this. Right? I'm going very fast, copying from the notes so I don't make any mistakes. Right? So I do this, compute the vector field. So let's write, so basically I need to write the strip condition. So the strip condition is PS QS equals to 1. Which amounts to 1 P minus Q times 0 equals 0. So PS equals to 1, and therefore QS equals to 1. Okay, so I'm going very fast on purpose because it's time also for you to double check. So strip condition, which we did at the beginning, so initial PDE, here's the PDE. Easy in this case. tangent vector normal to the normal vector. For this case, it reads like this. So therefore, from here we get P is equal to 1, and Q is equal to 1. So these are then basically our initial conditions, right? Because it's constant. Okay, agree? Right? It's constant. Sorry? Good? And then, I think one of you asked me, I forget, oh, how does the integral surface look like and so on? And I mentioned to you it was a plane. Okay? So it's here in the notes. And right, check. As an exercise that I recommend to you, because it's in the notes, and even if I have time, I can use 3 minutes and do it. I'm not going to do it, because try to do it on your own, to just integrate these things with this guy to find that, and I'll stop here, right? To find that u of xt is this. So it's just x plus t, right? So, right, here's like a picture from the notes, like a plane. You see just this dark thing. You have the Monge cones as we saw last time. So basically the Monge cones are all touching this big plane in x, t, z, right? The problem looked complicated. This one is fully nonlinear as opposed to quasi-linear, which is nonlinear, but we know what it means. The characteristic equation looked more complicated, but in this case was not, right? This is a more abstract problem. I myself don't know an application exactly for this problem. And we solve this. The solution comes out to be sort of simple, right? And do the details as a good exercise, right? At one point, I'll give you maybe a set of problems to exercise these things, but you get it from the books. And this is a good point for us to stop, and I'll come back next class. Let me see exactly if I have what I have in mind to refresh, which is, yeah, maybe one more example problem. And then I'll probably talk about, yeah, exactly, the wave equation and explain to you what I meant here by geometrical optics and how to, this variance is from a linear wave equation in, say, 2 dimensions. I extract a nonlinear problem out of it which is the icon equation, and it's for a situation like this where things vary, okay? And also soon I want to bring my laptop and give you a lecture that appears in the notes and so on before, but give you many examples of where all these things come in, okay? So, obrigado, and we'll come back next class.